Hello, uh, this is a recording on the module RSK4805. In this recording, I'm going to take you through part 1 of study unit 1. As you might know, this module is known as market risk, and it's got a number of learning units covering different topics, and it's based on the risk management and financial institutions textbook by John C. Howe. The way he explains things and takes you through risk management is really helpful, and he's also written a number of risk management textbooks. So I would advise you to go through this module together with the textbook and the notes and online classes I'll be giving you. So in this first recording, part 1 of this first recording, I'm going to take you through topic 1. And topic 1 covers learning units 1 to 3, and it introduces you to market risk management, including sources and challenges of market risk management and other concepts. So in this recording, I'm going to look at learning unit 1. Learning unit 1 is mostly based on chapter 1 of the prescribed textbook. So once you've gone through this recording, you can also look at chapter 1, which is an introduction. It's just a high overview of some of the concepts you need to know with regards to risk and return. And you can also look at the learning units notes, which is this, which are given on my UNISA. Okay, so I'm just going to take you through some of the important things you need to note from chapter 1 of the prescribed textbook, which is learning unit 1. But feel free to go through the concepts again by looking at the learning units and the prescribed textbook. Now, the first thing you need to note with regards to learning unit 1 is the importance of risk management in an organization and the function of the chief risk officer. A lot of the concepts in the earlier chapters, especially the theory behind risk management and the chief risk officer or the risk management function in a company, might be familiar with you from other subjects. If not, you will touch on them as you cover your other risk management subjects. So the first thing I'm going to look at instead is risk versus return. So I'm sure we are all familiar with what return is and what risk is. When we talk about return, we're talking about what you get back after investing in a particular asset or in a particular investment. And when we talk about risk, risk is the uncertainty associated with the return of the asset. So when we say an asset is risky, we mean that there's a lot of uncertainty with regards to the return that the asset can give us. And then there's something very important when we look at risk management and investment and finance. You need to always remember that the higher the risk taken, for example, the higher the risk of the asset, then the higher the expected return. Some books and some financial practitioners will say the higher the risk taken, the higher the required return. But it's also fine to say the higher the risk taken, the higher the expected return. And it makes sense that if you're taking on a lot of risk, you will expect higher return. You will expect a higher reward. You will never have a case where there's something with low risk and high return. Because if there's an investment with low risk and high return, everyone will run to that investment. And as they run to that investment, it will push the price of that investment up, and then it will reduce the return of the investment. So market efficiency always ensures that the higher the risk taken, the higher the expected return. This relationship always holds. If it doesn't hold, it means there's an opportunity and people will quickly take advantage of it, lowering the expected return to balance with the lower risk. So So you have to be able to calculate risk and return for an asset. So I'm going to take you through how we can calculate the expected return of an asset and how we can calculate the risk associated with an asset. Now, the formula to calculate the expected return is given right here. There are some symbols you need to be familiar with here. But basically, what this formula is saying, it's saying that if we have an asset that we wish to invest in, or an asset that we hold, if we want to determine the expected return, we simply take the probability of return in scenario I associated with the asset, and we multiply that by the return of the asset in scenario I. In other words, the expected return is a weighted average of the possible returns. This is better illustrated through an example, and let me show you an example of how to calculate expected return. Let's say you want to invest in equities. Equities are just shares, and let's say the economy next year, in 1 year's time, can have 5 possible states. Let's say state 1 with probability 0.05 is when the economy is very good. Let's say 0.25 is the state when the economy is just good. Let's say 0.4 is the state of the economy when it's just average. 0.25 when the economy is poor, and 0.05 if the economy is very poor. So these are probabilities associated with different states of the economy. And correspondingly, we have different returns associated with these different probabilities. So let's say if the economy is good, we get a return of plus 50%, and the probability of the economy being good is 0.05. If the economy, if it's very good, sorry. If it's just good, then it's 30% with a probability of 0.25. If it's average, it's a return of 10% with a probability of 0.4. So this is just summarizing the possible returns and the probabilities associated with those returns. So we can calculate the expected return of holding this equity by simply multiplying each probability times its return, 0.05 multiplied by 50%, right? 0.05 times 0.5 plus 0.25 multiplied by 30%, 0.25 times 0.3 plus 0.4 multiplied by 10%, 0.1, 0.25 multiplied by minus 0.1. So it's important to put this in brackets because we have a negative. Then lastly, 0.05 multiplied by minus 0.3. And then if we add this up, we get 10%, which is our expected return. So that's how you calculate expected return. It's a calculation worth practicing. You need to be familiar with your calculator. And when you're putting this into your calculator, you need to ensure that you put the numbers correctly. It's one of those calculations you can take for granted. What I can do is maybe just put a calculator up on the screen just to illustrate to you how you would input this into your calculator. It's important to be familiar with these things. There are things that we can sometimes take for granted, and then they come in the exam. Okay, so firstly, so you can follow this calculation if you have a similar calculator. The first thing we do is we say 0.05 multiplied by 50% plus 0.25 multiplied by 30%, sorry, delete, multiplied by 30% plus 0.40 multiplied by 10%, 0.1 plus 0.25 multiplied by open bracket. So we use this minus right here, minus 0.10 close bracket plus 0.05 multiplied by, and we use this minus 0.30. And we get 0.1, which is 10%. We can multiply that by 100 to change it to a percentage. So make sure you are familiar with that. So that's how we get the expected return. So I've shown you how to measure the expected return or how to calculate it. You also have to be able to measure and to calculate risk. You are going to see there are other ways to measure risk, and there are different types of risks, like systematic risk and unsystematic risk, but we'll look at that later in the chapter. But for now, at a high level, risk can be measured using a measure known as the standard deviation of return. Right? For now, when we talk about risk, we're talking about the standard deviation of return. So the standard deviation of return is a mathematical measure that tries to show us how variable, how risky, remember risk is variability of returns, how variable our returns can be. And the formula for the standard deviation of return, usually the standard deviation is given by this symbol, right? Sigma. The P just means standard deviation of asset P, but it's usually a sigma. Is the square root of E, the expectation of R squared minus the expectation of R all squared. This is just the expected return. It's just the expected return squared. And then this part, which says ER squared, is given by this formula right here. So it's given by this formula. Right? And this formula is simply saying that we square our return and we multiply our return with the probability for each state, for each possible outcome, then we subtract the expected return. Right? So what this formula is telling us, it's telling us that if we want to get the standard deviation of return, if we want to measure the risk associated with an investment, we take each return associated with the investment and we square it, then we multiply by the probability associated with that outcome, then we subtract the expected return squared. So I can illustrate this to you. And also please note, you find the square root of this answer. Before we find the square root, we call it the variance of return. But after finding the square root, it becomes the standard deviation. So in other words, if we just calculate what's inside only without finding the square root, we call that the variance of return. But when we find the square root, it becomes the standard deviation of return. So using our previous example, the example we had before, right? We can first calculate the variance, and then the square root of the variance will give us the standard deviation. And to get the variance of return, we take the first return of 0.05, this one, and then we square it and we multiply it by its probability, right? So we take the first return, we square it, and we multiply by its probability. And then let me just quickly correct that. I had squared the return. Let me square, okay, no, it's actually correct. The 0.05 is the probability. So we take the probability and we multiply it with the return squared, okay? Then we take the second probability of 0.25 and we multiply it with the return of 0.3 squared. And we keep doing that. Take each probability, multiply it with the return squared, then add the next probability multiplied by the return squared plus the next probability multiplied by the return squared. Be careful of these minus signs. Remember to put them in brackets. And then lastly, we subtract the expected return. Remember, we got an expected return of 10%. So lastly, we subtract the expected return squared. That will give us 0.036, and then the square root of 0.036. This is the variance. The square root of 0.036 gives us 0.1897, which is 18.97%, and that gives us the standard deviation of return. So this would be the risk. So at a high level, if we say calculate the risk associated with the asset, we're talking about the standard deviation of return. So you can put the recording on pause, just try to punch this into your calculator See if you get the same answer, right? The next thing you need to note in learning unit 1, you need to know about investment opportunities. When we talk about investment opportunities, when we're dealing with risk and investment management, we are talking about looking at the relationship between expected return and standard deviation for various assets. So investment opportunities can be illustrated through a diagram whereby we show expected return versus standard deviation for different assets. So the diagram below illustrates the relationship between risk and return for various assets. So this diagram is known as an expected return versus standard deviation diagram, and it's just showing us different risky investments, whereby this is one investment, maybe it has a standard deviation of 5%, and it's got an expected return this side maybe of 10%. So maybe the risk here is 5%, the standard deviation and the expected return is 10. We have another investment here. This one has more risk because it's to the right. Maybe its risk could be 10% and its expected return could be 20%, right? So these are just different combinations for different investments showing the expected return versus the standard deviation. We call those investment opportunities. And then as you can see, this diagram is going up, meaning in general, like what we said, the higher the expected return, then the higher the risk. You see, it's an upward going diagram. The points appear to be going up like that in an upward direction, showing that as our expected return is increasing, so is the standard deviation. Okay, so here I wrote, note the shape of the diagram. As risk increases, the expected return increases, and vice versa. So once you are familiar with this diagram, and once you're familiar with measuring risk and return for an individual asset, you now also need to be able to measure risk and return for a combination of different assets. Okay, I'll repeat that. So far, we've looked at measuring risk and return for individual assets. After being comfortable with measuring risk and return for individual assets, you also have to be able to measure risk and return for a portfolio. So a portfolio is now when you take a group of different investments of different assets and you hold them together. We might want to then calculate the collective expected return of all those investments, or the risk, the standard deviation collectively of all those investments. So in this module, for simplicity, they usually deal with two asset portfolios, right? We're usually dealing with two asset portfolios. So this would be the case whereby you just hold two assets in your portfolio, right? So for a two asset portfolio, the expected return is given by the following formula. W1 plus mu, this is mu, mu1 plus W2 plus mu2, giving us mu p. So mu p just means expected return of the portfolio. W1 is the weight invested in asset 1. What percentage of your money have you invested in asset 1? That's W1. Mu1 is the expected return of asset 1. W2 is the weight invested in assets 2. And mu2 is the expected return of asset 2. And please note, since you're just holding one asset, your total money is 100%. So if you invest 30% in asset 1, obviously what you invest in asset 2 is 1 minus 30%, which gives you 70%. So that's an example. So the weight invested in asset 2 is equals to 1 minus the weight invested in asset 1. And if we add the weights of our investment, we should always get 1, right? And then we also have the formula for the standard deviation of a two asset portfolio, which is given below. So the standard deviation of a two asset portfolio also involves a square root sign. So I think I should also illustrate how you would pick up a square root sign, because I took you through a previous example whereby you calculated expected return, but I didn't show you how you would find the square root, right? So let me just illustrate to you through a calculator. So let's say you get 0.036, which is the variance. I'm going a bit back and you want to get the standard deviation. The square root function is this one right here. So you would then just say 0.036, and then that would give you 0.1897, which is 18.97% if we multiply by 100. So this is the square root sign. So the same approach would apply when we are dealing with a two-asset portfolio. We first calculate what's underneath to get the variance of the portfolio, and then the square root of the variance would give us the standard deviation of the two-asset portfolio. So this is the formula for the standard deviation of the portfolio. Sigma 1 is the standard deviation of asset 1. We know W1 is the weight invested in asset 1. Sigma 2 is the standard deviation of asset 2. So we are squaring that standard deviation, right? W2 is the weight invested in asset 2. R1, so these are the standard deviations of R1 and R2. And then this is known as rho. It's like a P, but it's actually pronounced rho. It's from the Greek alphabet, this. And it represents what we call the coefficient of correlation. It's a measure of the relationship between our two assets, okay? So this is the formula we would use to get the standard deviation of a portfolio. But let's actually see how this would work. Let's say we want to create a two-asset portfolio. And let's say portfolio 1, actually, I was supposed to say asset here, right? For example, suppose we want to have a two-asset portfolio with asset 1. This is supposed to say asset 1. With asset 1 with an expected return of 10% per annum, and asset 2 with an expected return of 15% per annum. So we've got two different assets. This should say asset, sorry about that, with asset 1 with an expected return of 10% and asset 2 with an expected return of 15%. So the expected return of asset 1 is 10%, expected return of asset 2 is 15%. And suppose the standard deviations of the two assets are given before. Asset 1 is a standard deviation of 16% and asset 2 has a standard deviation of 24%. And suppose the correlation coefficient between the two assets is 0.20. So we can calculate the standard deviation associated with this asset. We can also calculate the expected return, but I'm just going to look at the standard deviation. So we would use this formula, right? So we can change, so let's assume we invest 80%, 0.8 in asset 1, and 80% of our money in asset 1, and we invest 20% of our money in asset 2. We can then substitute that information into the formula for the standard deviation. W1 squared plus the standard deviation of asset 1 squared plus W2 squared, the weight of asset 2 squared, times the standard deviation of asset 2 squared, plus 2 times W1 times W2 times the correlation. It's actually 2 times the correlation times W1 times W2 times the standard deviation of asset 1 times the standard deviation of asset 2. And that will give us 0.00215. Let's just check to see if we can do that, just to illustrate to you how you would actually do that calculation, just for practice. Okay. So you would take your calculator and you would clear it, right? And then you would say 0.80, this is the weight invested in asset 1 squared, times 0.16, the standard deviation of asset 1 squared, plus 0.20, weight invested in asset 2 times the standard deviation of asset 2 squared, plus 2 times the correlation between asset 1 and 2, times the weight invested in asset 1 times the weight invested in asset 2 times the standard deviation of asset 1 times the standard deviation of asset 2. And we get 0.02115. And then lastly, we can find the square root of that, and we get our answer of 15.54%. So that's how you would punch everything into your calculator. So the table below summarizes the different expected returns and standard deviations for different portfolios. So you can practice to see if you can get these values for different weights, for different values of W1 and W2. Try to see if you can find the expected returns of the portfolio and the standard deviations of the portfolio. I can illustrate to you how, I just calculated this, right? Let me illustrate to you how you would get this expected return. I've just shown you how you would get this 14.54. Let me illustrate how you would get the 11%, the expected return on the portfolio. Remember, we said the expected return on the portfolio is given by weight in asset 1 times expected return of asset 1 plus weight in asset 2 times the expected return in asset 2. So to get this 11%, we can use these two weights, 0.8 and 0.2, and we can use our expected returns of 10 and 15. So it's 10 and 15. 10 and 15. So we would say 0.8 times 10, this is the associated return of asset 1, plus 0.2 times 15, which is the expected return of asset 2, and then we get 11% as the expected return of the 2 asset portfolio. So just try to practice with these other ones. And try to see if you can get these values. It's good practice to be comfortable with your calculator. Right. So once you're comfortable with that, once you've calculated all these expected returns of portfolios and standard deviations, you might then want to put them in a diagram similar to this. This was a diagram for just investments only, right? Assets. We can also illustrate our portfolios on an expected return versus standard deviation diagram. And when we're dealing with portfolios with different weights, we usually get a diagram like this. The diagram will be sort of like a curve. You'll get this being the part that's to the furthest top left of your expected return versus standard deviation diagram. So as they say here, alternative risk return combinations from 2 investments. So this is just illustrating to us that for one portfolio, we can get an expected return of maybe around 16%, right? Which would be this one. And the corresponding risk would be maybe 10%, right? Sorry. 16% is actually here, so the expected return is to the left. So the expected return is the lowest at 10%, yeah, and then the risk is 16%. So this would be one combination. So we can plot those to show the alternative risk return combinations from 2 investments. So this is important. This diagram is really important because if you're trying to minimize risk as an investor, this diagram can help you to better understand the relationship between return and risk for a combination of different portfolios. So most investors will choose the portfolio to the furthest left as they are risk averse. So most investors will choose this portfolio right here because it's to the furthest left, it's got the lowest risk. That's what most investors will choose because they are risk averse, they want to avoid risk. And like I said, more investors will choose the portfolio to the furthest left as they are risk averse. Risk averse means you want to avoid risk. You'll only take on risk if there's a high expected return. That's how most investors are aware of risk. So most investors will choose the portfolio to the furthest left as they are risk averse and will want to minimize risk, which is the standard deviation. whilst increasing expected return. So in conclusion, that leads us to something really important known as the efficient frontier. So on a diagram of expected return versus standard deviation, we can get what we call an efficient frontier. So this is an example of an efficient frontier right here, okay? But I'll discuss it further right here. You'll see what I mean. An efficient frontier shows a group of portfolios. An efficient frontier shows a group of portfolios such that it's not possible to get a portfolio with a higher expected return for the same given level of risk, or a lower risk for a given expected return, and when compared to that portfolio on the efficient frontier. Okay, so let me explain what I mean by this statement. Let's say we have all these risky investments. These could be portfolios, they could be individual assets, right? Let's say we have all of these. And let's say we have other investments which are on this line known as the efficient frontier, right? So you can take that line to be similar to this line right here, to this line. Let's say we have that line and we have some investments there. If an investment is on this line, this efficient frontier, we say that that investment is efficient, right? And what we mean by that, we mean that if we are on this line, we can't go any higher. We can't get a higher expected return for the same level of risk. We can't get a higher expected return for the same level of risk when we are on the efficient frontier. Plus, we can't get lower risk for the same level of return. I'll repeat that. We can't get higher return for the same level of risk, and we can't get lower risk for the same level of return. That's what happens when we are on the efficient frontier. It means we've got the best portfolio possible given our risk and return preferences. Compare that with this portfolio right here, which is not on the efficient frontier. Let's assume this portfolio has a risk of 5%, right? And let's assume it has an expected return of 9%, right? This portfolio is not efficient because we can move up. We can move up to this portfolio, which is on the efficient frontier, which will still have the same risk of 5%, but it will have a high expected return, for example, maybe of 12%. So you see, for the same level of risk, we are getting a higher expected return, which means that this portfolio is not efficient. The same applies for all these other portfolios inside. The same would apply for this portfolio. We can get a higher expected return for the same risk. The same applies for this one, high expected return for the same risk. The portfolios on this efficient frontier are the best. We can also illustrate this. I illustrated it going up. We can also illustrate it going left, right? Let's say we invest in this portfolio. This portfolio is not efficient. Let's assume it's got a risk of 5%, right? And let's assume it's giving us an expected return of 9%, right? It's not efficient because we can move to the left. We can move to this portfolio. We can move to this portfolio right here, to the left. And then we can have less risk, which might be 3%, but still giving us the same expected return of 9%. So it means it's possible to get the same return for less risk, which would mean that this one is not efficient. And even this one for 3 and 9 is also not efficient because we can move left further still to come to this efficient frontier. When we are here, we can't move left anymore. This is when we are at the best, where risk might be 2% for an expected return of 9%. So we're getting the same return for lower risk, right? So on the efficient frontier, things cannot get better. You can't find a portfolio with a lower risk for the same return or with a higher return for the same risk. And then this efficient frontier, so far we've just been looking at portfolios and risky investments. we can move a step further and we can now introduce what we call a risk-free investment, an investment without risk. So if we now start considering our portfolio or our assets and we make it possible to invest in risk-free assets, for example, are assets like government bonds or treasury bills, we assume they have no risk. If we introduce risk-free assets into our portfolio or into the market we're considering, this efficient frontier, which is a curve, then collapses into a straight line. It becomes a straight line. So such that we now have the risk-free asset where it says RF being displayed on the expected return standard deviation diagram. So this is the efficient frontier of risky investments only, and this is the efficient frontier consisting all investments in the market, both risky investments and a risk-free investment, right? So the efficient frontier collapses into a straight line when we introduce risk-free investments, right? So here we say the two diagrams illustrate and compare the efficient frontier for a group of risky assets only and the efficient frontier for all investments. So this would be for all investments, right? So there's something important to note here with regards to the efficient frontier for all investments. We have a point M, right there. We call this point the market portfolio. And let me just read this. Point I is achieved by investing beta 1. So this is just a weight by investing beta 1 of available funds in portfolio M and the rest in the risk-free investment. Point J is achieved by borrowing beta J minus 1 of funds available at the risk-free rate and investing everything in portfolio M. The investment represented by M is referred to as the market portfolio. Okay, so I'm just going to finish up by explaining what we mean here. Now, since we've now introduced a risk-free asset, we get a straight line as our efficient frontier. And in economic theory, we make an assumption. So this is just a theory, okay? It's known as mean variance portfolio theory. There's a theory which says that people invest all their money either in the market portfolio or in the risk-free asset, depending on their tolerance for risk. If you're someone who totally doesn't want any risk, you would invest all your money in the risk-free asset. But if you're someone who's prepared to take on some risk, you can invest a proportion of your money in the risky asset and a proportion of your money in the risk-free asset. So I would be a portfolio where a proportion of your money is in the risk-free asset and a proportion of your money is in the market portfolio. J would be a portfolio where part of your money is in the market portfolio, but you then go and borrow, and then you even invest more in the market portfolio such that you end up at the top part of the line. So when you now go to the right of this line, it means you've actually borrowed money to invest more in the market portfolio. And portfolio theory, this is a theory, it's known as mean variance portfolio theory. This portfolio theory says that everyone will invest their money either in the market portfolio or in the risk-free portfolio. Like your money will be divided between the risk-free portfolio and the market portfolio. Everyone in the market will have their money either in different proportions in the market portfolio or the risk-free portfolio. And if for some reason you decide not to invest in the market portfolio because you think there are better investments somewhere else, maybe because an investment is cheap, if you move your money there, everyone else will pick up that investment is cheap and they will start buying that investment, which will push its price up, leading it to be properly priced, and then that will just lead you back to the market portfolio. So everyone holds their money in the market portfolio or in the risk-free asset in different proportions, depending on their tolerance for risk. So it's just something, it's a lot of financial economics, but it's something that's covered in the prescribed textbook, and it's also talked about in the learning unit. So it's just important for you to be comfortable with that, and it forms the basis for what I'm going to take you through next as I finish learning unit 1 on the capital asset pricing model and the arbitrage pricing theory. Okay, so you can read the textbook. John Howell does a really good job in explaining. If you just give yourself maybe 45 minutes or an hour to just read through that, it will help you to understand this further, but I've tried to summarize all the information as best as I can. So that brings me that brings me to an end with regards to this class. I hope it's been helpful. If you have any questions or queries with regards to what I've covered, please feel free to let me know. I won't always be able to get back to you promptly, but I'll try to do so as soon as I can. Thank you once again.